Hi, you guys. This is Mrs. Bolin with your notes for 9.3 exponential growth and decay functions. And so, as you remember, yesterday we looked at the graphs of the functions. Now we're going to look at the difference between whether the function is growing or decaying or getting smaller. So, but first, as some review, we are going to look at the percent as a decimal. And so remember that we move the decimal 2 places to convert from a percent to a decimal. So we have 0.04. You can put a 0 out in front there too if you want. And then for 35%, you would have 0.35. For 128%, you would have 1.28. And for 250%, you would have 2.5. You could either leave the 0 on there or leave it off because it's at the end. Sorry, my book was kind of sideways, so that's why it does not look like a 0. Okay, so just some information, you guys, about growth functions. So if you think about growing, that's something that's getting bigger and bigger and bigger. So if this base right here is greater than 1, think about 1 representing 100%. If I just multiply by 1 every time, it doesn't change. If I'm more than 100% of what I have, it adds a little bit at a time and gets bigger and bigger and bigger. Whereas if I have a decay function, that's where this base, the number that I'm multiplying by each time, is between 0 and 1, meaning that it is not a negative number, but it's smaller than 100%. So like if I'm multiplying by 75% every time, it's getting smaller and smaller and smaller. So, oh, there we go, focus, that helps. So for an example, if you have a number greater than 1, it's going to be growing. If you have a positive number that is smaller than 1, it's going to be getting smaller and smaller and smaller. And the way that we find the rate at which it's changing is we compare it to 100%. So remember how I said the number 1 is like 100% written as a decimal? Well, you look at it and say, okay, how much above 100% is it? Well, it's 75% added on top of the 100. So this is our growth rate. Whereas this one, if we're at 0.55, which is 55%, and you want to think, well, how much is that below 100%? So you'd go 100, take away 55, and we get 45. That's how much it is decaying. So we're always, always, always comparing with 100% because 100% means no change. If it's more than 100%, it's growing. If it's less than 100%, decaying or getting smaller. And so you're always asking yourself, how much above or below is it from 100%? Okay, if we have compound interest, that is if instead of just figuring out the interest at the end of the year, you take the yearly rate and divide it by a certain number of times, like quarterly would be 4, semi-annually would be twice, monthly 12, weekly 52. So we're just taking what's going to happen over the course of a year and divide it up into smaller chunks. And so we will get to that in a minute, but this one, the P is your principal or initial amount that you put in. That 1 represents 100%. And then the R is the rate that we're adding on, but we're dividing it by the number of times in that we're compounding it each year. The T is the number of years, and again, the N is how many times we're compounding it in that 1 year. So we are going to look at some problems here, you guys. So here's our practice problems. We're going to start off with some softballs here, nice and easy. So, you know, softball, like easy. All right. So this is getting multiplied by 2, multiplied by 2, multiplied by 2. So do you guys think that's growth or decay? Is it getting bigger? So this would be exponential growth. This one is divide by 3, divide by 3, divide by 3, which is the same thing as multiplying by a third. Divide by 3 or multiply by 1/3, same thing. Again, this is a positive number that's smaller than 1. So that tells us that the function is getting smaller and smaller by an even rate. So this is decay. Sorry, even ratio, not rate. Rate was for our linear equations. So now we're going to look at some other problems. we need to determine whether the function represents exponential growth or decay just by looking at the function. State the initial amount, A, and the growth or decay rate as a percent of change. So first of all, look at this. Is that bigger than 100% or smaller? Well, that's 107. So, right, we've got an extra 7% there. So this is growth. Okay, and the rate at which it's growing is 0.07, or you could say 7%. Okay, 7% growth. Let's look at this one now. That one is smaller than 100% because 100% would just be having a 1 there. So this one would be decay. Oh, and I just realized I forgot to give the initial amount. That's our initial amount, A. A would be 5. So assuming that we had 0 years, and we're just, remember, anything to the 0 is 1. So 5 times 1 is 5. That is our initial amount. This one, sorry, going back to part B, this one's decay. And because it's smaller than 1, but still positive. And then the rate would be 100% minus this. So we would get 0.52 or 52% decay. So the rate of change is, you might sometimes see it as a negative because it's going down. Okay, and this is 7% growth. And then our initial value here, A equals 6. I should have switched to a different color. Sorry about that. I will for number 4. Okay, so looking at problem number 4, same thing. We're going to say whether it's growth or decay, initial amount, what's the rate, and percent of change. Okay, so this one, first of all, here's our initial amount, A equals 0.75. Whatever number is outside of the parentheses there is our initial amount. And then this one is growing because it's bigger than 1. So we're going to say growth. And then the rate at which it's growing is the amount that it's bigger than 100%. So this is 1.36. The extra amount there would be the 0.36. Or you could say 36% growth. Okay, for this one over here, we have our initial amount A would be 0.5. And then this one is less than 100%, so less than 1, but still positive. So this is decay. And then we always compare it to 100%. So if I were to write this as a percent, it would be 99%. And compared to 100%, we went down by 2%. So R would be 0.02, or you could say 2% decay. Okay. Now we get into the ones that are a little bit trickier. We've got one of those compounding problems. So I'm going to start by writing our formula from the notes. Y equals P1 plus R over N to the NT. This is my initial amount, or principal. That's why there's a P used. You're like, I, why don't they just use I for initial? Well, it's P, it's our principal. How much did we deposit? Excuse me. N is the number of times compounded in a year. And then R is the interest rate in decimal form. So I'm just going to put rate. And then T is the number of years. And you will notice that N appears twice here. So now we're going to go ahead and write a formula for that. So it says you deposit $1,000. Okay, so that right away I'm thinking, okay, that's going to be my initial amount. So I'm going to write Y, which is the amount I have at any given time, equals the amount I put in. So if that's all I put in, that's where my account balance would stay. But I'm getting some interest on this, okay? So I know that I'm going to keep 100% of my money, plus I'm going to get some interest on there. Well, I know that my interest rate is 0.02. And if I were just doing this once a year, it would just be 1.02 and then to the exponent of how many years. But because I am compounding it monthly, that means that I'm going to take the amount that I'm going to get per year and I'm going to divide it into 12 chunks. Okay. Well, then I'm going to do that 12 times. every single year. So I'm going to put a T right there. Okay, so if I plug in now to this next question, I want to know how much money I'll have after 17 years. Okay, so if I were plugging that in, I would say y equals 1,000, oops, times 1 plus 0.02 over 12. And then I'm going to do this for 17 years. So we could go over to Desmos real quick and plug that in. And then let's go ahead and do that actually. So, oops. So I'm in a new tab. I'm going to go to Desmos.com, and I am going to go to the scientific calculator. And we're going to start plugging those values in. So I have 1,000. I'm going to multiply it by 1 plus 0.02 divided by 12. And then I'm going to raise it to the power of 12 times 17. Okay, and so we got look at my $1,000 has grown just by leaving it in the bank. So I'm going to write this down on my paper and I'll show you in just a minute. So we have y is equal to, and remember this is money, so I'm going to round it to the nearest penny. So I have 1,404.55. And so that's where I'm rounding it because we want to think about the context here. So I'm going to go back over to my Elmo, and you can see that that's the amount I wrote. Now the question is a little bit of an extension is what if we compounded it quarterly instead of monthly? So how would that change? So I'm going to switch colors here again. So I'm going to use the same exact formula, but everywhere I plugged in a 12, think about that was monthly, how many times a year for monthly. So we're going to plug it in for quarterly. Well, that would be 4 times a year. So I'm going to copy the same exact formula. Y equals 1,000 times 1 plus 0.02, it's 2%, that's right. And then I am only compounding it 4 times a year. And then I'm still going to do that for 17 years. Okay, that's a little dot for times there. That's not a decimal. So I'm going to switch back over to Desmos, and we're just going to change our numbers just a little bit. And so if we look at that, instead, everywhere there's 12, I'm going to put in a 4. And I'm going to change this 12 to a 4. And so now we get our total there. I still have a lot of money, but not quite as much as when I compounded it quarterly instead of monthly. It went down by less than $1. But if you had a big number, that would be significant. At this point, it's not, but it still is different. So we're going to write that down. Y equals, again, I'm going to write it as dollars and cents. So I have $1,403 and I have 76 cents. Okay, so we're going to go back over to the notes for today. So as you can see, it makes a little bit of difference. Over time, that difference would grow, or like I said, if we had a different principal amount there, like let's say $1 million, then we would start talking about things that are a little bit more meaningful than just a few pennies. Okay, so let's go ahead and look at your assignment for today. Here we go. We're just going to do the odd ones. And then you guys can try the even ones on your own. So first we need to decide, does this represent growth or decay, or neither? It's possible that it doesn't change at a constant ratio. So if I do 50 divided by 10, I get 5. So I did divide by 5 here. If I divide those, I would get 5. And if I divide those, I would get 5. So this does have a constant rate, a constant ratio, which makes this exponential decay. And then if we look at the next one, I did -4, -4, -4. This one is neither because it is linear. Remember, anytime, sorry, my writing is kind of sloppy there. Anytime we add or subtract the same amount every time, that's a linear function with a constant rate of change. We're looking for, in the exponential situation, a ratio. So meaning that if I divide this number by this number, I get the same answer every single time, okay? If we look at this one, and I divide 51 by 17, that would give me 3. This one would give me times by 3. This one would give me times by 3. So this does have a common ratio. This would be growth, exponential growth. Oh, I did number 2. Man, you guys, sorry. You got an extra free one in there. Okay, so looking at problem number 5, this one says determine whether the function represents exponential growth or exponential decay, then state the initial amount. So I'm going to start with the initial amount, a equals 3. Then I'm going to look at this and see, am I keeping 100% of my value, or is it going to be below 100% or above 100%? Well, this as a percent would be 75%. So I am not keeping my original amount. I'm going down. It's lower than 1, a positive number that's lower than 1, in between 0 and 1. So this is decay. And then, and I'm imagining right here, you guys, that these t's are supposed to be little exponents. Because if I were just timesing by t, that would be a linear function. I'm guessing that was just a little glitch with our printing. So pretend like those are little exponents up there. Doo-doo. Okay. And then decay, blah, blah, blah. And then the rate as a percent of change. And so it wouldn't be 75, okay? What we're doing is we're starting at 100% and we're saying, how much did we go above or below 100%? So if I'm at 100% and I'm comparing it to 75%, I went down by 25%. Okay, so you could say that the rate is 0.25, or like the rate of change is negative 0.25, or you could say that it's 25% decay, or you could say negative 25% because it's going down. I don't know. Okay, as a percent of change. So then we are going to go ahead and look at number 7. So this one, the initial value is 17. And then the rate, yeah, this one I would have said over here that the rate was negative 25% because it's subtracting off of 1. This one we're going to look at and see, oh, it's growing, right? Because it's above 100%. Well, what is the rate that's being added on? 2%, or you could say 2% growth. Okay, we're going to skip number 8. We're going to go right on to number 9. So this says a $900 sound system decreases in value by 1.9% each month. Write a function that represents the situation. Okay, so depending on if you had X is the number of months, or if we're looking at like compounding per year where we want to plug it in, there's a couple different ways to write this depending on how you define your variables. So we could write this as, I'm going to show you both ways, but you could write this as y equals 900, and then you could just have, if it's going down by a percent and a half, and I start at 100%, I'm going to take off 1%, I'm at 99, I'm going to take off another half, I'm at 98.5%. And remember, we always write it as a decimal. And then I could put m, where m is the number of months.